Hi, we're going to start this concept called slope fields. And the good news is slope fields is very weird. And the other piece of good news, slope fields is very easy. So as we start to go through this, you're going to think, what the heck is going on? But by the time we get to the end, you'll say, I see it. And you might be able to say, I literally see it. So if you look at this situation, you have what looks like a differential equation and this thing called the initial condition. And the instructions for a problem like this in the slope field world would say sketch the slope field and the solution curve through the given point. Well, the first thing we're going to do is sketch that slope field. And for that slope field, we're going to concentrate on this, which you might say is a differential equation, but you also might say it's a derivative. The derivative, dy dx, is 1/4 x squared. So in other words, this is a formula for the slope at any point I care about. So since it's a formula for the slope at any point I care about, I'm going to make an unusual t-chart. You're used to plugging in an x value and getting out a y value ever since 6th grade. But now we're going to plug in an x value and get out a dy dx, or a slope value. And that makes sense because if I would put in a 2 here, 1/4 times 2 squared would give me an output of 1. 1 equals dy dx. In other words, my output is a slope. So I've taken the time to make this t-chart. These are the various x values I'm caring about for this example. And when I plug any of them in, my output is a slope value. Now, for the purposes of these examples, we're going to go through the extensive t-chart, but you wouldn't always have to do all these numbers. So let's take a look at what does this t-chart really mean. So to begin with, I'm going to take a look at this spot on the t-chart. When x is -2, dy dx, or the slope, is 1. So I go over here to this unusual coordinate grid, and the x value is -2 right here, and here, and here, and here, and here, and here, and here. Any dot in this column has an x value of -2. And that's saying that at x equals -2, the slope is 1. So what I'm going to literally do, I'll take any of these dots where x is -2, and I'm going to draw a little slash that represents a slope of 1. It's on the trajectory where if I went up 1 over 1, up 1 over 1, up 1 over 1, that's the trajectory of this slash. So at x equals -2, my slope is 1. Well, that's a spot where x is -2. But there's another spot that x is -2, and there's a spot down here where x is -2. So what this really means is for every x value of -2, I need to represent a slope of 1 with this little slash. That slash is just a visual representation that the slope there is 1. So I could do this in another spot. Let's take this one. When x equals 3, the y value is 9/4, but that's not really a y value, it's a slope value. That slope value is a little bit more than 2, and lucky for us, we don't have to be super precise. You do have to be precise, just not crazy OCD precise. So here's an x value of 3 right there. I'll use that one. If the slope is 9/4, that means I need to draw a slash that's on a trajectory up 9 over 4. That's just about 2, so I'm going to use this as a good marker right up there and draw that slash. And now I'd have to keep doing that. At any x value of +3, draw a slash with a slope of about 9/4. What I would need to do is carry this out for all of these, and after I do that, I'm going to get this kind of neato web. And you see it down here. This is the slope field for that differential equation. You'll notice that at any x value, there's a slash that approximates that slope. Well, let's not worry quite yet about what this actually represents. But now let's do this. The instructions also said sketch the solution curve through the given point. So here's my given point. It says f of 0 equals 2. In other words, 0, comma 2 is a point. So I'm going to go to my completed slope field, and I'm going to put a point at 0, comma 2. And now what I need to do is just imagine that these are kind of like the currents of a stream. And if I dropped a stick in these currents, what way would the currents want to take it? So I just kind of follow, and this is again not super precise, but you do need to be reasonably accurate. Right here at this slope of 0, the currents are going kind of horizontal, but as I head to the right, you see the currents want to start heading upward, or the slopes want to start heading upward. So I just kind of approximate how would this stick flow through these currents if I were to do this, and heading in this direction, it would head that way. So what I've done is I've just drawn basically a reasonable path that follows the slopes for that slope field. That's the solution curve. We're going to come back to this situation later in the video to show how all this stuff can even come together even more. But we're moving on to a quick other example here for a moment. I have a different differential equation or a different derivative and a different initial condition point. The directions would still be the same: sketch the slope field and the solution curve through the given point. I don't need to go in depth as much, but a couple things to point out. I'm going to make a t-chart, and notice I have to input a y value to get out a slope value. So instead of x comma y or x comma slope, I have y comma slope. And we'll just pick one spot. Let's just pick this one. This says when the y value is 2, the slope is 3. So now I have to think about this differently. This entire column over here is where the y values are 2. This is a y value of 2, so I sketch a slash that represents a slope of 3. If I had chosen this one, when the y values are negative 2, oops, that's right up there, I would need a slash that's down at a trajectory sloping at negative 1. And as I look at this, I could have completed more, but eventually, these slopes get so steep, it almost feels like you're drawing a vertical line for this type of resolution that we have here. If we needed to draw the solution curve, we need to take a look at this spot. This is basically saying we have the point 0, comma 1. So there's 0, comma 1. And if I were to just let the currents take me away, it would end up looking like that. And now I didn't fill these out up here, but I know from my t-chart that the slopes are just going to get steeper and steeper and steeper. So the solution curve would look something like that. And like I said with the previous one, we're going to come back and add a little bit more to that. But I want to show you one other twist that could happen to you in a slope fields problem. If you take a look at this one, you'll notice now that your slope is generated by inputting an x value and a y value. That's going to have implications to your t-chart. And that implication is you can't just plug in an x value to get a slope, or you can't just plug in a y value to get a slope. You have to plug in an x and a y value to get a slope. So I'm choosing a few at random. If x is 2 and y is 4, my slope is 3 because I plug into here. So that means at the point 2, comma 4, there it is, my slope that I would have to sketch would have to be a positive 3, which would look something like that. Well, unfortunately, if I were to fill out this whole entire slope field, I would have to go literally do a calculation for each one of these points. I wouldn't be able to follow patterns like I do in those previous ones. Don't worry, the AP is never going to make you fill out a complete grid, and especially in a situation like this, they won't make you fill out a complete grid. For something as complicated as this one, they might just circle a certain portion of the grid and have you fill it out. Let me point out a couple of unusual spots. At the coordinates 0, comma 2, which are right there, If I take these values and plug them into the slope generator, the differential equation, I end up with a 0 in the denominator, which makes an undefined slope. So you could mark that with a 0, or you could mark it with a vertical line, because undefined slope in algebra is sometimes represented by a vertical line. I think putting a 0 there is the best thing. And then in a case like this, if I plug in an x equals 3 and a y equals -2, I end up with a dy dx of 0. That means a slope of 0. So at x equals 3, y equals -2, that's that spot right there, my slope is 0, which is a horizontal line. We're not going to go through the pain and agony of doing the calculations for all of these, but if I would, I could come up with a nice little web of slashes, a slope field, for that differential equation. And we're going to finish up by taking a look back at what we started. So for this example, we filled out this primitive t-chart and we got the slope field and we got the solution curve. But I want to show you how it connects to the differential equations that you are now an expert at. If I take this differential equation, or first derivative, or slope formula, and this point, I can treat it exactly like a differential equation, and I can solve that differential equation. No need for me to over-explain the steps, but I've gone through separation of variables, solve for y, solve for c, and I get this graph, y equals 1/12 x cubed plus 2. Hey, wait a second. When I solve this differential equation, the graph or the equation that I got is the equation that should match this solution curve. The solution curve depends a little bit upon your judgment, but this should be darn precise. And now it kind of makes sense, because if you remember from your families of functions, this is a cubic function which kind of has this type of wavy pattern. So my slope field gave me an overall picture of a wavy pattern. Should have probably told me, hey, you're working with a cubic style function, quite possibly, and then solving that differential equation confirms what my suspicion was. So with that being said, when I look at this one and I look at the solution curve that I ended up drawing, I say, hey, that kind of looks like exponential growth. It's a rocket ship blasting off up to space over here, and over here we're coming in for a gentle landing, almost like that's an asymptote. Well, when I solve that differential equation, my suspicions are confirmed. There is my differential equation, and I go through separation of variables, solve for y, solve for c, and I end up with 2e to the x minus 1, and this is the graph of 2e to the x minus 1. So the slope field and the solution curve are very, very related to the differential equation. You could say the solution curve and the slope field are the artistic version of solving a differential equation.